Okay, welcome everybody to this lesson. It's an important one. We're going to talk about periodicity assumptions and computing annualized yields to maturity. So very important topics. Now, what's the issue here? Well, whenever you quote the yield to maturity, so when quoting the YTM, that YTM should always be annualized, so quoted on a per annum basis, per year basis, and it should be appropriately compounded. And how you arrive at that annualized and compounded YTM will really depend on an assumption that you need to make. Depends on the assumed number of interest periods during the year. And that basically means that assumption is called the periodicity assumption. This is what we call periodicity, and typically what it's going to equal is the frequency of interest payments or coupon payments on a bond. So if a bond pays coupons quarterly, you will assume a periodicity equal to 4. If it pays coupons semi-annually, then 2, and if annually, then 1. Okay, it's best to really examine a question in order to get your head around all this. So we're going to do a question which you see on the screen right now. The annual yield to maturity for a 7-year 6.4% semi-annual coupon bond trading at 97.24 per 100 of par value. This shouldn't be R, it should be is closest to. Okay, so what's the annual or annualized yield to maturity for a 7-year bond? Because it pays semi-annual coupons, we're going to assume, this is a rule, a periodicity of 2. So let me write this down. For semi-annual coupon bonds, the periodicity you have to assume is 2, unless you're told something different. This is going to be typical for bonds coming from the US and bonds coming from the UK, which are the two countries where you'll typically find coupon payments being paid twice a year indeed. Now, in order to do this on the calculator, which is what we're going to do effectively, is you have to input the following things. For N, it's a 7-year bond, but because we're thinking in terms of semi-annual periods, you multiply that 7 by 2, so you input 14. Now for PV, for the present value, the price, you just take this 97.24, but make sure to make it negative. Now for FV, we're going to have a nice and simple 100, and then make sure you get the coupon input right, the PMT input, because they tell you it's 6.4, but you need to divide that by 2. 6.4 divided by 2 is going to give 3.2. Once again, everything has to be in line with the assumption of working on a semi-annual basis. So let's take the calculator, do second followed by FV to clear the time value of money worksheet first. And now let's do these inputs. 7 times 2, 14. That's going to be my N. Then 97.24 plus minus key to make it negative. That's the input for PV. 100 is my FV, and I've got 6.4 divided by 2, 3.2. That's my PMT input. Compute I over Y. So CPT I over Y, the calculator returns an answer of 3.45, which by the way is one of the answers. It is answer A, isn't it? But it would be the wrong answer. This is the yield per semi-annual period. It's not the annual yield that we were asked about. And in the exam you'll always be asked about the annual or annualized yield. So this is the yield per semi-annual period. And in order to turn it to the true answer, we need to multiply by 2 times 2. That gives 6.9. That is our true annualized yield. So that's the annualized yield, or simply the annual yield. Okay, so annual or annualized yield. And when computing, like we did over here, an annual yield or annualized yield, annual YTM with an assumed periodicity equal to 2, which is what we had as a result of this bond being a semi-annual coupon bond, you get a result which is known as the semi-annual bond basis yield, annual bond basis yield, or the semi-annual bond equivalent yield. Please be aware of these names. Your book does stress them as being quite important, to understand what they mean by this. So it's a yield where you take the yield. It's an annual yield which you compute by taking what you computed for a 6-month period, the semi-annual yield, and multiplying that by 2. Right, that's the first question. Now the second one is going to relate to zero coupon bonds, because with a zero coupon bond, because it doesn't pay any coupon, there is realistically, you don't have any idea of what the periodicity should be for a zero coupon bond. So here's the question: the annual yields to maturity stated with a periodicity of 2 and 12 for a 3-year zero coupon bond trading at 87.83 per 100 of par value are closest to. So the thing is, if you are presented with a zero coupon bond, or indeed something called a strip bond, which I'll tell you about in just a moment, you will have to be given a periodicity to use to compute the YTM, the yield to maturity. Okay, once you're given a periodicity, you can do the computation. So let's start off with a periodicity, or the periodicity of 2, which is the first one on the left-hand side over here. Right, it's a zero coupon bond with a 3-year life to maturity. So the only thing you have to do on your calculator is say, okay, 3 years times 2, the periodicity, that's 6 semi-annual periods. The PV is minus 87.83, because that's the current price of the bond over here. We know that FV, the future value, is simply the par, that's 100. So let's take the calculator, second FV, to clear the time value of money worksheet. I've got my 6 for N, 87.83 negative, that's the PV, 100 FV. Because I cleared the time value of money worksheet, I should have nothing sitting on the PMT. Now compute I over Y. Of course, if you didn't clear your time value of money, you'll probably have something sitting there from the previous problem. Okay, let's see what it is. It's 2.186, but this is once again the yield per semi-annual period. I need to multiply that by 2 to get myself up to a annual yield. This is the bond equivalent. Or the we wrote down semi-annual bond basis yield, or the semi-annual bond equivalent yield. Now this 4.37%. Okay, let's do the same thing with a periodicity of 2. To be honest, sorry, not with a periodicity of 2. We've already done that with a periodicity of 12. To be honest. The first result, 4.37, narrows the choice down to A or C, and you can tell which one is going to be the right one simply from the relationship of the numbers. But let's do this properly. It's going to be very quick on the calculator, because all the inputs are the same apart from the N assumption. Here it's going to be 3 years, but now times 12. So 3 times 12, okay, that's 36. That's going to be our new assumption for N. So let's click N over here. The rest of the stuff, the PV and the I over Y, are exactly the same. So I can just do CPT. Sorry, the PV and the FV are the same. So I can compute I over Y. 0.361% times 12. Okay, 4.33%, and that should be in line. Yes, okay, it's absolutely in line with answer A. Now, how could you have gotten this answer without doing the second computation? Well, because of that relationship. Let's say over here that if compounding and periodicity is the assumption about how frequently you compound interest. So if compounding is more frequent, then a lower annual rate or a lower annual yield to maturity is, let's say, enough to produce the same overall result as would a YTM computed under a less frequent compounding assumption, right? So you could have known this was correct. This cannot be correct. When you've got a higher periodicity, you're going to need a lower yield. Okay. Now all right, let me just go back to a moment here. I talked about this case of zero coupon bonds being similar to strip bonds, so let me just say a few words about that. What you can do is you can create what effectively is a zero coupon bond out of coupon paying bonds. So if you take a coupon bond, a bond that pays coupon, a coupon here, a coupon here, a coupon here, a final coupon here, and principal as well on its maturity date, what institutional investors can do is they can buy this bond, which is basically a package of future cash flows, and you can strip it apart. You can take this cash flow and turn it into an individual bond. You can take this cash flow and turn it into a separate security. So a security which has, 1, 2, 3 years until maturity, and on its maturity date it promises this much. This coupon will be turned into a 1-year zero coupon bond. So you buy bonds, but you strip them apart and you turn each little cash flow into an individual zero coupon bond. So the same stuff that I said here about zero coupon bonds applies also to strip bonds, which are effectively zero coupons created out of coupon paying bonds. You will have to be given a periodicity assumption. Now, the final bit which you need to know on this topic is how do you go about, or how do you convert between yields or rates with different periodicities, effectively different compounding assumptions. Okay. If you've got a bond that pays a semi-annual coupon and a bond that pays an annual coupon, how can you basically compare their YTMs if they're computed on different bases? Well, that's what this question is all about. A bond is trading at an annual yield to maturity of 5% computed on a semi-annual bond basis. The bond's effective annual yield and the annual yield to maturity computed with quarterly periodicity are closest to. Okay, now we've got options for both, and let me just clarify that the effective annual yield, which is mentioned over here, this is the YTM of the bond, the yield to maturity with a periodicity assumption equal to 1. Okay, that's simply the effective annual yield, and the yield to maturity computed with a quarterly periodicity is obviously computed with a periodicity assumption of 4. Now, what you ought to appreciate, and what's at the bottom of all these computations, is the following equation, the relationship. 1 plus the APR. Now, APR is used in this section of the curriculum, stands for annual percentage rate. But this is basically the same as yield, right? Computed with a certain periodicity, let's make that periodicity m, divided by m to the power of m. I know it sounds very sort of elaborate here and difficult, but it's not. Equals 1 plus this, the APR, it's not the same APR, computed with another periodicity divided by that frequency to the power of n. So, if in the first part of the question we're asked the bond's effective annual yield is, well, periodicity assumption should be 1. And we're also told that computed on a semi-annual bond basis. Remember, semi-annual bond basis, we kind of wrote that down somewhere here. It means with an assumed periodicity of 2. So, right, what I could do is say, what I can say is the following. If I know that 5% is the yield on a bond, so 5% expressed in decimal format is this, semi-annual bond yield, meaning with a periodicity of 2, well, 1 plus this to the power of that is the same as 1 plus the effective annual yield with a periodicity of 1 simply, of course, divided by 1 to the power of 1. But, you know, this dividing by 1 and taking to the power of 1 adds nothing here. So I can basically say that the effective annual yield equals 1.025. I've taken the 5% and I've divided by 2 to the power of 2, but minus 1. Let's see what that gives. 1.025 squared minus 1. Okay, that's 5.06%. Good. Nice. That's the correct answer. It's either A or C. Now, the thing is, we could have known it's 506. Because it couldn't have been 2.5. How do I know it? Because if you've got a YTM, a yield to maturity, computed with a periodicity of 2 that equals 5, to get the same result but with less frequent compounding, you need a higher YTM. This is kind of going back to what I wrote here. If compounding more frequently, then you need a lower YTM. But if you're compounding less frequently, like here, just once, periodicity equals 1, it has to be higher than 5, so it had to be either A and C. Now, hopefully you can get what the quarterly number should be, because once again, it's all about the relationship with compounding. Okay, for everybody else, let's do it sort of properly on paper. So what I can now say is, using the same relationship, 1 plus 0.05, that was the semi-annual bond basis yield, so divided by 2 to the power of 2, assumed periodicity of 2, equals 1 plus a yield, an APR with quarterly compounding, divided by 4 to the power of 4. And let's say this is 1.025 squared equals 1 plus APR divided by 4. I'm actually going to take this, exponent to the power of 4, and I'm going to get rid of it by taking the root from both sides. So I'm going to say, okay, 1 over 4 over here on the left-hand side. And now it becomes quite simple. The APR, assuming quarterly compounding or a periodicity of 4, equals 1.025 squared to the power of 1 over 4. I need to deduct the 1, and I need to multiply everything by 4. It should be fine. Now let's see. 1.025 squared first, okay, and then to the power of 1 over 4. So I'm hitting the y to the power of x button and opening a bracket, 1 divided by 4 close bracket equals minus 1 times 4. Okay, that's 4.97, thereabouts, 4.97%. Let's check the result. Yeah, it has to be answer C, doesn't it? Because with a more frequent compounding, the YTM doesn't have to be as big. So that just confirms the previous rule, which I already wrote down. Now, do go and check out in your curriculum the questions or the examples, which also, there's one example utilizing a negative yield. If you want to do that, please go ahead if you've got the time. You know, quite recently, especially in the Eurozone, we had negative yields, so there is an example on that, doing this computation when the APR is actually negative. If you don't have the time, don't bother about it. It's the same computation, just using a minus number. Right, thanks for watching. Join me for the next video.